Dear students, we will discuss about the chemistry of F block elements. So before going to the topic, first of all, let us know about what are F block elements. The elements in which the valence electron enters into the F orbital or anti-valence shell are known as F block elements. So F block elements are also called as inner transition elements because they are the transition elements within the transition elements, that is D block elements. That's why they are called as F block elements. So based on the valence electron whether enters into the 4f orbital or 5f orbital, they are classified into two types. They are 4f orbital or 5f orbital. Based on that, the F block elements are classified into two types. One is lanthanides and the other one is actinides. Lanthanides means the valence electron enters into the 4f orbital. They are known as lanthanides. If the valence electron enters into the 5f orbital, they are classified as actinides. So coming to the lanthanides, in lanthanides the valence electron enters into the 4f orbital. So that's why they are called as lanthanides, and they are also called as first inner transition series. Lanthanides are also called as first inner transition series or lanthones also, because they are immediately comes after lanthanum, the element lanthanum, which is present in the D block element. So there are 4 lanthanides from cerium to lutetium, and these 4 lanthanides lie in between lanthanum and hafnium in the third D block transition series. So coming to the actinides. So what are actinides? In which the last electron or the valence electron enters into the 5f orbital are called as 5f block elements or actinides or second inner transition series. They are also called as actinides because are actinides, actinoids, because they are coming immediately after the actinium. That's why they are called as actinides. So these actinides are radioactive. Almost all the actinides are radioactive and lie below the lanthanides. So from here, actinium to rubidium. So coming to the electronic configuration. So what is the general electronic configuration of F block elements? The general electronic configuration of F block elements is N-2 F1 to 14, N-1 D0 to 1, Ns1 to 2. So this is the general electronic configuration of F block elements. Suppose if I take 4f block elements, that is lanthanides, from cerium to lutetium, that is cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, amium, terbium, thulium, ytterbium and lutetium. So these 4 are considered as 4f block elements which are coming after lanthanum. That's why they are called as lanthanides. Next, the other classification is 5f block elements, that is actinides. They are coming after actinium, that's why they are called as actinides. From thorium to lawrencium are considered as 5f block elements or second inner transition elements. Thorium, protactinium, uranium, neptunium, plutonium, americium, curium, because the pronunciation is very important in the case of F block elements. Berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. So these 14 elements are considered as 5f block elements or actinides. So now let us discuss about the oxidation states of lanthanides. So what is the oxidation state? Whether they exhibit +3, that means the lanthanides exhibit variable oxidation states, but among them the most stable and common oxidation state that is exhibited by lanthanum is +3. But lanthanides also show +2 and +4 oxidation states due to the presence of or due to the stability of either half filled or completely filled or empty 4f subcells. Suppose if I take cerium +4, which is more stable because it is due to noble gas electronic configuration after losing 4 electrons from cerium. and ytterbium and terbium. Ytterbium in +2 oxidation state and terbium in +4 oxidation state are more stable due to half-filled f orbitals, that is 4f7. And ytterbium in +2 oxidation state, it is more stable because it is having completely filled f orbital, that is 4f14. See, if I take ytterbium, see in ytterbium in +2 oxidation state ytterbium, that means by losing 2 electrons in 6s orbital, it get the electronic configuration of 4f14, which is a completely filled f orbital. That's why in +2 oxidation state ytterbium is more stable. And also in europium, see europium +2, europium +2 is also more stable because of half filled f orbital. After losing 2 electrons from 6s orbital, europium has 4f7 electronic configuration in which the f orbital is half filled. So that's why it is a more stable electronic configuration. That's why it exhibits +2 oxidation state. And also in terbium, see, let us see terbium. See terbium. Terbium, the electronic configuration is 4f9, 5d0, 6s2. After losing 4 electrons, that is from 2 electrons from 6s orbital, 2 electrons from 4f orbital, it exhibits +4 oxidation state, and the electronic configuration of terbium in +4 oxidation state is 4f7, that is half filled f orbital. That's why it is also more stable. So terbium in +4 oxidation state, it is more stable. But most of the lanthanates exhibit stable oxidation state, that is +3, but due to the half filled, due to the presence of half filled or completely filled or empty 4f subshells, they may exhibit sometimes +2 or +4 also. Now coming to the oxidation states of actinides, unlike lanthanates, that means lanthanates exhibit a few oxidation states, but actinides show a variable oxidation states from +3 to +6. Why? Because of the small energy gap between 5f, 6d and 7s subshells. So the energy gap between 5f orbital, 6d orbital and 7s orbital is very less. So due to that reason, actinides can lose electrons very easily from 7s, 6d or 5f. So because of that, they can exhibit variable oxidation states from +3 to +6. But the principal oxidation states of lanthanides or actinides exhibited is +3 and +4. So in the +3 oxidation state is the most stable one, but in some elements like thorium and plutonium, they may exhibit +4, which is the most stable oxidation state. And in protactinium and neptunium, they may exhibit +5 oxidation state. And in uranium, the +3, we can see +6 oxidation state also. So the oxidation states of actinides are very uneven. So magnetic properties. Let us know about the magnetic properties of 4 F-block elements. Actually, the magnetic property is mainly due to the presence of unpaired electrons present in the orbitals. If I take lanthanum +3 or cerium +4, ytterbium +2 and lutetium +3, they have no unpaired electrons. So they are all diamagnetic. When an ion, atom or substance becomes paramagnetic, the paramagnetic property of atoms, ions or molecules is due to the presence of unpaired electrons. But these ions or these elements in their particular oxidation states have no unpaired electrons. That's why these are all diamagnetic. And other lanthanide ions have unpaired electrons in 4f orbital. That's why they are paramagnetic in nature. So the magnetic behavior in lanthanides is due to the contribution of both spin movement and as well as orbital magnetic movement. Unlike the d elements, therefore the magnetic moment mu is defined as √4s s+1 plus L into L+1, where s is the spin quantum number and L is the orbital quantum number. But in the case of d block elements, only the magnetic momentum is due to the spin movement only. But in F block elements, the magnetic moment arises due to spin quantum number and as well as orbital quantum number. In case of lanthanides, the spin contribution and orbital contribution coupled together to give a new quantum number J, which is known as total angular momentum quantum number. So J is equal to L minus S when the orbital is less than half filled. When the orbital is 4f orbital is less than half filled, the total angular momentum quantum number is defined as J is equal to L minus S. When the orbital is less than or more than half filled, then J is considered as L plus S. So magnetic moment values for lanthanides in Bohr magneton is given by mu is equal to G into root over J into J plus 1, where G is called as Landé splitting factor and it is given as, and that means G can be defined as G is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J into J plus 1, where J is the total angular momentum quantum number and S is the spin quantum number and L is the orbital quantum number. So basing on this formula or using this formula, we can calculate the magnetic moment values for lanthanides. So now let us discuss about the most important topic, that is lanthanide contraction. So what is lanthanide contraction, or how can we define lanthanide contraction? So lanthanide contraction means the atomic size or the ionic radii of tripositive lanthanide ions, that means in +3 oxidation state, the size of lanthanides decreases steadily from lanthanum to lutetium due to increasing the nuclear charge and electrons entering into n-2 f orbital. This gradual increase in the size with an increasing in the atomic number is called as lanthanide contraction. That means in +3 oxidation state, from lanthanum to lutetium, the size decreases gradually with increasing the atomic number. This is defined as lanthanide contraction. Then what are the consequences of lanthanide contraction? So because of lanthanide contraction, following points will clearly conclude. One is atomic size and the other one is difficulty in the separation of lanthanides, because all the lanthanides almost in the same atomic size, we cannot separate the lanthanides. So effect on the basic strength of hydroxides of lanthanides and complex formation and ionization energies. So first one is, what is atomic size? Size of the atom of third transition series is nearly same because of lanthanide contraction. Example, suppose if I take zirconium and hafnium. So zirconium and hafnium are of similar size because of lanthanide contraction. And as well as niobium and tantalum are in the similar size due to lanthanide contraction. And the second one is difficulty in the separation of lanthanides, as there are only small change in the ionic radii of lanthanides because of lanthanide contraction. All the ions in their oxidation state have similar chemical properties. So because of their similar chemical properties, we cannot separate them very easily in the pure state. That means the separation of lanthanides is difficult because of lanthanide contraction. And the next one is effect on the basic strength of hydroxides. As the size of lanthanides decreases from lanthanum to lutetium, the covalent character of hydroxides increases. That means from lanthanum to lutetium, size decreases, the hydroxides covalent character increases. Whenever the covalent character increases, the basic strength decreases. Thus from lanthanum hydroxides are more basic and lutetium hydroxides are least basic because of lanthanide contraction. Next, complex formation. Because of the smaller size and higher nuclear charge, tendency to form complexes increases from lanthanum +3 to lanthanum +3 to lutetium +3. And as well as electronegativity, it increases from lanthanum to lutetium. Ionization energy. Attraction of electrons by the nuclear charge is much higher, as because the size decreases from lanthanum to lutetium, the ionization energies are much larger than 4D and 3D series. They have much large ionization energies. So similar to lanthanide contraction, actinide contraction also is there. The atomic size or ionic radii of tripositive actinides, ions decreases steadily from thorium to lawrencium due to increasing in the nuclear charge, and electrons entering the inner n-2 f orbitals. This gradual decrease in the size from lanthanum to lutetium with increasing the atomic number is known as actinated contraction, like lanthanate contraction. So this is considered as actinated contraction. So coming to theories of bonding in metals. So the following theories are given to explain bonding in metals, because metals have some peculiar specific properties. So the specific properties of metals is due to the presence of bonding. So what kind of bonding is present in metals, and how can we explain the nature of bonding in metals? So by using three theories, we can explain the nature of bonding in metals. One is the free electron theory or electron C model. It is also considered as electron C model, valency bond theory or resonance theory, molecular orbital theory or band theory. So by using these three theories, we can explain the nature of bonding in metals. So first one is the free electron theory or electron C model. So this theory was proposed by the scientists Drude and Lorentz. That's why this theory is also called as Drude-Lorentz theory. So according to this theory, all the atoms in a metal have several vacant orbitals in their outer shell. The metals have the tendency to lose some valency shell electrons to form positive ions are called as kernels. So according to this, what is the first point? All the atoms in a metal have several vacant orbitals in their outer shell. So each, suppose if I take sodium, what is the electronic configuration of sodium? 1s2, 2s2, 2p6, 3s1. So sodium has vacant orbital 3s2, 3s1. That means 1s2, 2s2, 2p6, 3s1, 3p, 3d. That means vacant orbitals are there in sodium. So in sodium metal, there are number of atoms are there, and each atom has vacant orbitals, and all together several vacant orbitals are present in the sodium metal in their outer shell. Suppose if we take sodium, let us see. What is the electronic configuration of sodium? 1s2, 2s2, 2p6, 3s1, 3p, 3d. So 3p, 3d are vacant. So just like number of vacant orbitals arises in the sodium metal, so these metals have the tendency to lose some valency shell electrons to form positive ions are called as kernels. So by losing one electron, sodium metal, by losing one electron from 3s orbital, it forms Na plus ion, which is called as kernel. So these kernels occupy closely packed fixed positions, and the valence electrons free to move throughout the volume of the metals. So these kernels like this, see, these positively charged are nothing but kernels. Na plus, suppose if I take an example of Na plus, sodium positively charged. So these are Na plus ions, and these electrons, these are fixed. These Na plus ions are fixed. These are fixed. The kernels are fixed, and the electrons are movable. So these electrons are called mobile electrons or delocalized electrons. The movable electrons, that means the positively charged metal ions, which are called as kernels, they are fixed, and the electrons are moving in and around the positively charged ions. So the movable electrons are called as mobile or delocalized electrons. Thus metals can be compared to an assembly of kernels immersed in the sea of electrons. That means one metal or any sodium metal or any other metal can be considered as an assembly of kernels which are immersed in the sea of electrons. So he considered that the electrons are considered as sea, and in the sea of electrons the metals are that means the kernels are fixed. So this is the electron C model according to free electron theory. So by using free electron theory, we can explain the following properties of metals, the following specific properties of metals, like thermal conductivity. Metals are good conductors of heat. Electrical conductivity, that means metals are good conductors of electricity. Malleability and ductility, and metallic luster, elasticity and hardness. So these specific properties of metals can be explained by using free electron theory. This theory explains these specific properties of metals. One is thermal conductivity, electrical conductivity, malleability and ductility, metallic luster, and elasticity and hardness. But What are the limitations of free electron theory? So this theory does not explain the semiconductance of metals, and it is also cannot explain the specific heats of metals. So the free electron theory fails to explain the semiconducting property of metals and as well as the specific heats of metals. So next one is valency bond theory or resonance theory. This theory was proposed by the scientist Pauling. According to Pauling, the metallic bond has partially covalent character and involving in resonance. We know that in a metal, each atom is held to 8 or 12 more atoms. However, the metal does not possess sufficient valence electrons. Consider the metal lithium. Suppose if I take lithium, which is a body-centered cubic lattice. See, this is body-centered. That means the atoms are at the corners of the cube and one atom is at the center of the cube. That's why it is an arrangement of body-centered cubic lattice, and in this arrangement each lithium atom is in direct contact with 8 other lithium atoms. See, each lithium atom is in direct contact with 8 other lithium atoms. See, here one lithium atom and it is in contact with 8 other lithium atoms. 1, 2, 3, 4, 5, 6, 7 and 8. Thus each lithium atom requires 16 electrons for the formation of covalent bonds with other 8 lithium atoms. So in order to form the bond with this lithium atom, it requires 2 electrons. 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 So such way, 16 electrons are required for each lithium atom to form 8 covalent bonds. But lithium has only one valence electron. That means and has only 9 electrons are available for bond formation between 9 lithium atoms. Each lithium atom is having one valence electron. So in order to form covalent bonds between 9 lithium atoms, it requires 18 electrons, but 9 lithium atoms have only 9 valence electrons. Then how it is possible? So this discrepancy can only be explained on the basis of that each covalent bond between 2 lithium atoms resonate between various atoms like this. Resonate. This lithium forms bond with this lithium once, then it withdraws the electron and forms bond with this lithium like this, resonance in lithium. So this is how the valency bonds, that means covalent bonds, are obtained or formed between 9 lithium atoms with 9 electrons only because of the resonance. So this is resonance structures in lithium crystal lattice. Next, molecular orbital theory or band theory. According to molecular orbital theory, in a metal, the outer atomic orbitals of large number of metal atoms overlap to form large number of molecular orbitals. The outer atomic orbitals of large number of metal atoms overlap to form large number of, suppose if I take sodium or lithium, s orbitals. So the s orbitals of all lithiums overlap to form large number of molecular orbitals. Or sodium, the 3s orbitals of all sodium atoms overlap to form large number of molecular orbitals, and which are delocalized over the metal atoms and crowded together to form a band, like a band. See, when the metal orbitals overlap to form molecular orbitals, one bonding, one anti-bonding and one non-bonding and so on. The molecular orbitals merge into one another to form the bands. The bands containing the outer shell electrons are called as valency bonds, and the vacant or partially filled bands are called as conduction bands. So the bands, that means some are bonding, some are non-bonding and some are anti-bonding. So these are considered as bands, and bands in which the outer shells have electrons, outer shells have electrons are called as valency bonds, and the vacant or partially filled bands are considered as conduction bands. In metals, conduction band is close or overlap to valence band, therefore they are good conductors. So the metals in which the conduction band is closer to or overlap, the conduction band is close, very close or overlap to valence band, then the metals are considered as good conductors. If the gap between the conduction band and valence band is very large, that metals are considered as bad conductors. Suppose if I take iron etc. are good conductors, because in these metals the gap between the conduction band and valency band is very less. They are very close to the conduction band and valency band are very close to each other in such a metals. They are good conductors of electricity. But in non-metals, the energy gap between valency band and conduction band is very large. Hence, they are non-conductors or bad conductors. For example, if I take carbon, in carbon, the energy gap between valency band and conduction band is very large. So, it is a bad conductor of electricity, or it is a bad conductor. But in semiconductors, the energy gap between the conduction band and valency band are not very close or not very large. So, they are mediumly space is there between the two bands. At room temperature, these are not good conductors, but with increasing the temperature, they are good conductors. Suppose if I take germanium, in germanium, the energy gap between conduction band and valency band is not very large or not very close. That's why at room temperature they are bad conductors, but with increasing the temperature the conduction also increases. So semiconductors are also prepared by doping an insulator with a suitable impurity. Such type of insulators are called as extrinsic semiconductors, and these are all two types, N-type and P-type semiconductors. N-type semiconductors means when the impurities of group 15 added to the semiconductors, phosphorus and arsenic, they are nothing but N-type semiconductors. P-type semiconductors means when the impurities of group 13th added to semiconductors, example boron and aluminum, these are called as P-type semiconductors. See, we take an example of here the valency band overlaps with the conduction band. Here the valency band overlaps with the conduction band, and in this diagram the valency band is very close to the conduction band. So these are the good conductors. These metals are the good conductors of electricity. These good conductors, but here the energy gap between valence band and conduction band is very large. That's why they are insulators, they are non-conductors. But in this, the energy gap between valency band and conduction band not very small or not very large. So small energy gap is there. So at low temperature they are not considered as conductors, but with increasing the temperature the conductance also increases. So they are considered as semiconductors. So with this neat diagram we can explain the molecular orbital theory.